All right, everyone. Thank you for tuning in, and everybody on YouTube, or welcome. So, a couple of housekeeping announcements. First, we are looking for speakers. So, if you want to give a talk like this, if you'd like to have NASA endorse YouTube video, please either shoot Aaron or myself an email. We're happy to get people for the coming academic year. Um, we sort of been habitable worlds, astrophysics focused in the last year or so, but we're absolutely, or 2 years. Oh gosh. But we're absolutely here, happy to hear any extragalactic like astronomy talks. We are absolutely thrilled to hear from Taylor Hutchison, one of my favorite Sears people. She got an NSF GRFP to work with Casey Popovich, got her PhD in 2022, and then is now doing a NASA postdoc. So, stellar career so far. Sears collaborator, and we were promised a unreserved pitch for an habitable worlds instrument. So I'm very curious which one and two, or sorry, unreserved or unhinged. One of those two, one of the U's. And so I'm very keen to hear what this is going to be. So without further ado, Taylor, take it away.
Thank you so much. Hi, everyone. Let me share my screen. Yes, and I hid my tabs so you can't see all of them. Cool. All right. So thank you, Bennett. This is going to be an unhinged pitch for putting a specific instrument on Hab Worlds, and you'll understand by the end of this exactly which instrument I want there to be. And so to kind of motivate this, I'm going to be showing you some just a slew of gorgeous data from JWST from a number of different programs I'm part of. So we're going to explicitly talk about, I think we should put an integral field spectrograph on HWM. I honestly don't really care what the wavelength is. I think a UV one would be amazing, but honestly, we just need one. And I'll prove why. And I think that the type of physics you can do with this is almost enumerable. And if you had one for every wavelength, oh my God, even better. So with JWST, we have this really gorgeous imaging of all of these beautiful lensing fields, and we have this amazing level of sensitivity. I mean, this is one of my favorite images from, the very first image shared from JWST way back in, I think, 2023 or 2022. And it was just wild to see this level of detail. And I think nowadays when we're seeing these AI-driven images and stuff, this almost lensing fields almost look to me like you've asked an AI to make a galaxy field because these little noodles and squiggles of light don't look real to me. But this is all real, and this is all gorgeous, and this is gravitational lensing kind of acting like a cosmic telescope where it's zooming in on these very distant sources and kind of giving you this type of resolution that without lensing you only get with galaxies that are right next to the Milky Way. So here's a gorgeous example of a nearby galaxy that is not lensed, and we see with even before JWST, we were seeing beautiful structure within these sources. But with the advent of JWST, and specifically in this case, the MIRI instrument, which is, the more mid-infrared wavelengths, we're seeing a beautiful detail. We're seeing individual star-forming regions everywhere across this source. And this is just one of the many sources targeted. The FANG survey has an exquisite, kind of catalog of all of these types of massive nearby galaxies that have all of this amazing detail and resolution. And some of these sources, many of them of these nearby sources have been targeted by previous, surveys and previous telescopes. And so Manga had this gorgeous, massive survey where they were targeting as part of SDSS, this kind of integral field spectrograph in this like little hexagonal shape for all of these nearby sources. And so I'll explain in a second really what an integral field spectrograph is. But the point is that they were able to get these like individual star forming regions, the kind of the information about them that you would only get through this type of imaging for these nearby sources. And they were getting spectroscopy as well. And so I guess the question that I really want you to think about as I show you the answer to the question throughout the rest of these slides is, can we do this in the high redshift universe? And specifically, as spectroscopy is my bread and butter, can we do this type of like high spatial resolution spectroscopy in the high redshift universe that we've been seeing for decades now at lower redshifts? So we're going to kind of take a little walk, a little meander through cosmic time. And so to start us, we're going to be over, oops, yeah, we're going to be over here. right around redshift 1, about 4.9 billion years after the Big Bang. We'll be going earlier back in time as we move. So to start, one of the ways that people, canonically can try to, kind of spatially resolve star formation at higher redshifts is when you have these gravitationally lensed sources, they're kind of extended across the sky like these little noodles. And if you were to lay down a lot of different slits using like a multi-spectrograph, like MOSFIRE with KEK1 or NearSpec with JWST, you could, kind of get an insight on, across this arc with these little slits placed down, the different properties you see. And so this particular case, they're showing the R23 and the O32 values for different points along this arc. And you can see that, within uncertainties, they're actually kind of different depending upon where on the arc you're looking. And you might notice in this image, we have, A through D located, and then both 1 and 2. And these are mirrored images in the wonky way that gravitational lensing works. But this means that you're looking at individual little knots of star formation in this redshift 1.3 galaxy. And so what if you could get even better spatial resolution? And so as a kind of the way I like to describe IFS or integral field spectroscopy is you can kind of think of it as like every single pixel in an image has a spectrum. And so the way that this works is this three-dimensional cube. You have both your spectral information and your spatial information. And so one way I like to visualize this is with some gorgeous data from one of the ERS programs I'm part of, which is called templates, where we just took this beautiful IFU data of some, star-forming galaxies across cosmic noon. And what you're seeing here is this one source at about redshift of 4. And what we're doing is on the left-hand side, we're walking through the integrated spectrum as if you were to just place down a slit, one slit on this galaxy and get an integrated spectrum for the source. And we're walking through the N2 and H alpha emission lines. On the right-hand side, we're actually walking through the wavelength slices of the IFU data. And so you're essentially just seeing the image as a function of wavelength, each slice as we walk through. And so you'll notice as we walk through H alpha, for example, you see this gorgeous movement of where the emission light is coming from as a given, function of wavelength. And you also see, keen observers might notice there's this little light that pops up on this bottom left corner that is actually a companion source that we didn't really know existed before we got JWST data on it. It was one of the first papers published from IFS data for JWST. Just because I love showing these off, we're going to look at another galaxy from the same program. The source is around redshift of 3. And what you're seeing here is, again, we're walking through H alpha and N2. And so you're seeing this gorgeous movement. And you can get kind of this velocity information, this kinematics information from this data as well. So to kind of, show you some of the first data we got from JWST in this realm, this is from the templates ERS program, like I mentioned before. And the vision of this was to cover, across the peak of cosmic star formation. So all around redshift 2, but kind of going from redshift 1 up to redshift 4. And just these different star-forming galaxies, some which were HST dark, as you can see with the two on the right. They were only visible with ALMA before. And then the two on the left are really bright. They were definitely seen to HST, but they also have tons of little clumps and little knots of star formation. And so generally we tried to choose them that had really strong magnifications, expected to have some, a good range of star formation and other values. And so it's kind of a really good test case for what can we do with this telescope. This is the near chem imaging. And I'm going to click back and forth a little bit so you can really appreciate. I feel like sometimes people mistakenly compare HST and JWST as if they're the same, as if it's an apples and oranges. But really, it's more, this is gorgeous resolution and at a higher wavelength, right? Like this is where the power of JWST really comes in. And working with HST is really where that power combines. But the exquisite improvement in resolution is definitely something we should take advantage of. And then also we targeted these same sources with MIRI. And so you can see even just from the comparison of the near infrared wavelengths and the mid infrared wavelengths for these sources, you're seeing very different kinds of information pop out. I think the most striking example is the leftmost source, this is SDSS 1723, where you're seeing this almost flip in color depending on the wavelength that we're looking at. And so this is the type of information we can start to piece out. And so naturally we did put an IFU pointed at each of these particular sources. This is just showing a particular slice in the IFU based on the H alpha emission. And it is very beautiful. And I've spent a lot of my time staring at this. And there's a lot of analysis that's currently ongoing with this. But to show, just to highlight a few works from early career people in the program and to kind of motivate why this is so cool and what you can do with this. This is one of the first papers from our program. And this was led by Jack Birkin, who's a postdoc at Texas A&M. And this was for the two, higher redshift sources on the right-hand side here, these two SPT sources. And what this is showing essentially the metallicity for the first time in these dusty star-forming galaxies at these redshifts. So this metallicity was probed by the N2H alpha ratio, which, anyone can throw caveats at that, but it was the first time we were even getting just a gauge of the way that this metallicity might change across the arc. And one of the really cool parts, again, another visualization of how IFU works, is each of these points, again, is a spectrum. And so here on the right, I'm showing you for this really bright region that suggests really high metallicity compared to solar, what those profiles look like. And in this particular case, there's a really interesting possible additional component in these particular pixels. And so there's, some question on what might be driving that in this particular region. Are we seeing maybe the hint of an EGN over here? And so obviously, you could imagine like the slew of extra data and science that can be done with just the same IFU cube. For the other two sources in the program, I'm finishing up some work kind of playing around with the nebular ionization conditions. And so just as an example, here's the O3 over H beta ratio, the other part of the BPT, where you're seeing, again, really this gradient across these different sources. And it is really important to note that even with, the amazing advantage that lensing gives us, this is still really hard to do. Like some of these sources are still going to be really faint. And so you got to tease out as much light as you can. And so the source on the left is honestly, I'm still shocked we got anything from it. And it's really exciting that we have scientific results on this because this is, even though it's gravitationally lensed, it is still fairly faint. And so getting this kind of science is really exciting and really only possible with JWST. As another example, we're looking at that same noodle from Redshift 1.3, but I've just zoomed in on particular regions to show you on the sulfur 2 doublet literally how this density is changing across these different pixels. And it's really exciting because, as you can see on this, very useful diagnostic on the left from Danielle Berg's work in 2018, we have, showing a few different doublets that are very sensitive to the density conditions of the gas and how this doublet ratio changes as a function of density. And so you can literally see, from the two different pixels I'm pointing at with these arrows, that the density is changing. And so we're literally seeing across the span of just a few pixels across this source, changing density conditions in this galaxy, which is really exciting. Another thing that we can do is, in this particular work, which is gorgeous, very exquisite, very challenging, detailed work from Grace Olivier, who's a postdoc at Texas A&M, is getting actual direct metallicity indicators like aurora lines detected in the spectroscopy in this IFS data, and being able to actually come up with, these direct metallicity measurements for this particular source. And so you're kind of seeing this across the arc. This very exquisite, very challenging detail that kind of shows the range and the spread of metallicity within its individual source. And again, you can think of it these lower redshifts, the source is really right next to us in the Milky Way. We're able to, figure out, okay, these star-forming regions, this is how they seem to be evolving. This is how the galaxy is comprised, how it's evolved over time. We're now able to start to, take this information we're gleaning from these higher redshift sources and start to pick together that story as well. So now we're going to jump a little bit further back in time. We're going to go closer to around redshift 4. This is the LEGGOS program. And so this is a Cycle 2 program I'm part of that is actually a combination of two different Cycle 2 programs. The PIs are Gaurav Kohler at UW, Michael Florian at University of Arizona, and Matt Bayless at University of Cincinnati. And the vision of this was, a combination of 85 hours of gorgeous imaging and spectroscopy using the IFS near spec on JWST. And the goal here was, these are in this gorgeous little logo made by Sedona Price at UPitt, the 6 different sources, which I'll show you here as well. And they all were just very different types of highly magnified galaxies from redshift 2.3 up to almost redshift 4. And they all were chosen to have a ton of different little clumps, little bright knots inside of them that could potentially be, these knots of star formation or something else. And so we targeted it with both the prism spectroscopy, IFS, and then also a medium grading. And so we could both get, the general SED of these sources through spectroscopy, the gorgeous near-cam imaging, and then also better with a medium resolution, pick apart the actual profiles of these emission and the physics we can pull out. And so as a note, one of these is actually from a Cycle 1 program. This is archival from Emil Riviera Thorsen, who's over at University of Stockholm. And then the other is from the Templates ERS program, that really faint source I showed you before. So the thought here is, with these particular sources, again, kind of leveraging this ability with gravitational lensing, you can kind of individually study these little individual star-forming clumps in these lensed galaxies. And so what you're seeing here is this reconstruction actually using HST data from one of the targets in this program. And you're seeing this reconstruction, the little knots and the little knots of star formation, and how, maybe this is what the actual source looks like that has not had the light been lensed around this massive star cluster. And so you can start to kind of break back and go back to the source plane, which is what lensing people call it, and figure out where all of this light is located in this galaxy and what that might be telling us about how this galaxy is evolving. So for those who aren't used to gravitational lensing, sometimes the unlensed source plane images look like this. And so it's a little bit wonky, but it's still kind of the vision is, you'll see a little bit more of like a clumpy blob of a galaxy versus this long string noodle of light. And so what you're seeing here is one of the sources. We have amazing data from this program. And the contours you're seeing in green are this minimal H alpha emission across a few of these clumps. These other regions don't have as strong of the H alpha emission. And what's interesting here is, possibly we're seeing, these merging little post-starburst regions. We could maybe see, oh, the papers didn't show it properly, but you can, maybe see different regions where there might be these, stronger Balmer breaks in some of them versus, the stronger H alpha. And so you're literally seeing different types of star formation and different star formation histories in these different knots in this galaxy. And so what I'm showing you here is the same source. We just kind of rotated it for your eyes. And the bottom left in red is, the stellar continuum. And so you just by eye can note where all of these different clumps are for this source. The middle map is showing very strong H alpha emission. And then the right map is showing where there's really strong Balmer breaks. And they're not always coincident with each other. And so you're actually seeing literally these different clumps that have different types of star formation histories actively happening. And the spectra on the right are just showing a few of these representative clumps from both of those maps. And so we got this, even in a single galaxy, got a really gorgeous slew of information. All right. Again, this is an unhinged rant. We're going to continue moving forward. I'm going to now jump back even further. We're going to go back almost to the beginning of the end of the epoch of reionization. So right around 1 billion years after the Big Bang. This is actually my favorite source. Um, this galaxy is this massive lensed red arc. It actually covers about 12 arc seconds across the sky. It's so intensely gravitationally lensed. And it also happens to look a little bit like something that we remember from, our childhoods. And so we, for some reason, call this galaxy the Wazark. I don't know why, but this is the particular source. This is from ground-based imaging, which is how it was originally found. This is with HST follow-up, where you're already starting to really get this gorgeous detail of these different channels of light, these different knots. You can definitely see where light is being even more intensely lensed in certain parts of this arc. And then we got cycle one time on this source, and we used JWST NearChem to get even more exquisite data. And so this is a color image you're seeing using JWST NearChem imaging. And I've noted a few different places here. Based on the way that the lensing works, you're actually seeing three different images of this galaxy in this big smiley arc. The counter image is on the left-hand side. With these types of lensing, you can kind of see that it's almost like the image of the galaxy when it wasn't lensed. And then some of these circles are really interesting. So this white circle I have here is actually based on the gravitational lensing, a 75 parsec clump. And so at redshift 5, with this type of intense gravitational lensing, you're getting really to the sub-kiloparsec physics. You're able to resolve down to these real, like sub 100 parsec regions of star formation. And so just to show you a few interesting little maps from some work I'm finishing up, with this type of data, right, this type of IFS spectroscopy, you can get measurements for each of these pixels using, measuring the spectral features that you care about. And so using some strong line indicators, like 032 in this example, kind of probing ionization, you can then see on the right-hand side for pixels where we do have this coverage, there is an interesting trend and spread of this ionization. And what you might note, which I'll also show you a little bit later, is in these particular knots, these green knots that you see here, this is H alpha emission for this particular source that's been, demagnified for the lensing. But these are where the knots of star formation are. And so intriguingly for this particular source, we're seeing actually a dip in ionization where the star forming knots are, and then kind of a raise in ionization on the edges. And so something wonky, weird, interesting is going on in this galaxy. We're still kind of picking apart what that might be. Just to show you a few more little diagnostics that we have here. Um, when you have this type of spectral data, you can, even with the really faint stuff, try and measure things like the sulfur 2 doublet. I know I showed you a gorgeous example before of really boom-in lines. You could see by eye the change in that ratio for the doublet. In this case, the light is much fainter for these particular spectral features, but even still, we're able to get some, idea of the way that this density, the overall values, and then also how this is changing across the arc. And just for reference, on the right-hand side is showing, this histogram, and this is really just showing the amount of, values of that particular density. And so you can see we actually have a pretty good spread here, mostly clustered though around, a few hundred per cubic centimeter. But what's something else that's really interesting to note here is the solid black line on the histogram and the dotted black line are the total spatially integrated spectrum, as if we were to just lay a slit down on this galaxy, versus the median of the spatial information. And so you can see that, when you're able to zoom in on these galaxies using the combination of gravitational lensing and an amazing space observatory like JWST, you can actually get more accurate information about what's actually going on inside this galaxy across the galaxy versus what just a single spectrum globally averaged would tell you, which, would mostly be biased by the brightest regions and it might be hiding a lot more interesting information. Additionally, the more canonical thing people look at first is, the star formation and how this maps across the source. Um, this galaxy is very much, not super star forming. We've identified it as, this gorgeous post-starburst galaxy right after the epic reionization. So there's a lot of things that could be said for how this source got to this point. It's so early in the universe. Like, how did it become post-starburst by redshift 5? That's barely a billion years after the Big Bang. What evolutionarily happened to it as it, grew and formed and, existed throughout the epic reionization. And so stay tuned. There's a lot of really fun physics we've been throwing at this to kind of pick that apart. Um, but just to kind of show you, if we were to zoom in on some of those, like, sub-kiloparsec clumps in this particular source, um, what I'm showing you here is just like the type of, just like a family portrait of physical conditions you could look at here. And so I've already shown you most of these before, but you have star formation, two different types of metallicity indicators, ionization, and density. What's really interesting here is, first of all, the metallicity indicators are different. This isn't super wild because you could, if you talk to people who this is their bread and butter, they'll complain about N2H alpha for eons. But you were seeing at the very least like this gradient. There is definitely a difference in where these star forming regions are, the type of metallicity measured, and the type of ionization measured. And so we're kind of putting together this really interesting picture of the history of star formation in this galaxy and how it might still be proceeding, and then what's happening in the regions where there isn't a lot of star formation. Um, I could talk forever about this, so I'll spare you that. But this is really exciting, and this is the type of science we're able to start to pick apart. And so, all of this to say, I really want to highlight. I realize this was a pretty quick, like, unhinged talk, and the whole point is all of this is to show you the type of really awesome physics you can do, and that we've been able to do with JWST using these integral field spectrographs. But then, more specifically, imagine all of this. I'm going to go back to. Um, Whoop, all right, bear with me. I'm going to go back to, we can stare at this map in particular. So imagine if you were able to get this level of detail, but for, using a new observatory that has even better instrumentation because it's newer, that was maybe looking at the UV, the observed frame UV is, honestly what I want Haberls to do. Imagine if you could get this level of detail from nearby sources in the IFU. I mean, the UV canonically has always been really hard to measure. We have the costs on HST, but we're not quite sure how long that's going to last now. It's really challenging to get this kind of physics. There's been some beautiful work done by certain teams, for decades now, working on trying to understand the rest frame UV properties of nearby extreme sources to help us understand how, these higher redshift sources exist when we can't really get that level of sensitivity and detail. But at the same time, imagine if they could also have an IFU, so they could really deeply study the kinematics inside of these sources, look for turbulence, look for, literally changing density as a function of like 100 parsecs from each other. The type of science and physics you can start to do, it almost feels like we could start to be even more like comparing to these, really gorgeous SAMs and hydro simulations that get down to these really tiny scales. We could actually have data that kind of are starting to approach those scales as well. And so all of this to say, I think at the very least, there should be an IFU on HWO, but I would love to see a UV or rest optical one because I think this would be really powerful And there's a lot of other physics, talking about massive stars and we don't even have spectra of some of the massive stars. So how are we making these stellar populations at high redshift? I could go on forever about this. But all that to say, and you got to deal with me going back. Yeah. So all that to say, when you have this IFS data, you can get these spectra of the different regions. You can look at the velocity gradients. And so in this particular region, we're looking at the H alpha emission line and kind of comparing it as with the total redshift for this source. And you're seeing this velocity information. And this is also really important when it comes to gravitational lensing, because not only are we, just getting this information for the source in general, but for the lens modelers, especially in these really challenging fields where you need to know the redshift and, dynamics of every single source in the field of view to properly measure like the way that the physics is being warped by this gravitational lensing. These types of maps are invaluable. And this is really only something you can do when you have something like an IFU. And so I'm just going to zoom in on this while I close up my thoughts. Um, but really, this is I used to be a single slit spectroscopy person. I've obviously been converted thanks to JWST. I think the combination of JWST and Hab worlds would be really powerful, the same way that HST and JWST are really powerful together. I understand that Hab worlds is more defining the instrumentation based on the needs of the community and the science of the community. And so I think if more people are noisy about this, maybe they'll want to try and figure it out. Um, but yeah, so overall, after this very unhinged ramble, my pitch is we should put an IFS on HWO. Hopefully I've convinced you by now as well. I obviously kind of ending within the 30 minutes so that we can have a lot of time for discussion. I'd love to talk even more about this. But before I end, I actually want to do a quick shout out. I do this in talks where um, I like to give a moment to, kind of highlight key early career people who do a lot of unspoken labor and collaborations. Because often, that's not something that really like translates to a CV necessarily or to a job application, but this is critical work done in these communities, like data reducing, processing these data, being on call at all times to like fix problems with the pipeline or with, the catalog or help other people do their science. And that's not necessarily always like spoken out loud or acknowledged out loud. And so these are some amazing early career people that I work with who are, integral to the collaborations they're part of. They're kind of the backbone of these collaborations. And so I wanted to take a moment to highlight them. Feel free to take a screenshot. They're all amazing people. If they're on the job market, you should hire them. But yeah, so I will end this here and open up to our discussion and how I can continue to convince you that this is important. Thank you so much.
Fantastic. I don't think that was I think that was a very hinged talk. Yeah, I have questions. I always do, but I also um, would like to open the room first and then start dominating the question list like the gray-haired person that I am. So anybody have questions for Taylor, please ask them. How many people are in the room?
Or just opinions, Doesn't have to be a question. You can tell me if you agree with me.
I count 2 dozen potatoes and then I start asking questions. So first
Hang
things
on,
first.
there's a
Oh,
hand.
no, there's a question. Yes, excellent. See?
Hi.
Yes.
Hi. So I was just wondering, what do you think that is the ideal redshift that I mean, would be able to like study with an IFU on HWO? Like, what would be the redshift that you would, focus things on?
Yeah, it's a great question. So I actually like my PhD was in the epic reionization. So redshift 7 back then I used to think was really high redshift. I recognize now when people say that is low redshift sometimes, which is offensive. Um, I there's a part of me that wants to say we should focus there, but that would be near infrared. I think JWST has got that covered. I I do think actually like the redshift I'd want is maybe local or anything where we can still use the UV, like the observed frame UV wavelengths, because I think that is that is a regime that we actually still haven't really taken advantage of to its full extent. Like obviously we've done as much as we could in like the past, 3 decades that DHST's been around and even before that in some cases, but like I think having an IFU specifically with those regimes, there's still physics we don't fully understand, and I think we won't be able to unless we have this type of data. So I guess that means Redshift 0, and I'm betraying former me, but but I think lower than Redshift 1 is probably the right Redshift range for that particular type of science.
Yeah. Okay, thank you.
Yeah.
All right. The dam has been broken. Please ask questions, or I will jump in. Brad.
Hey, great talk. I just had a question if you had any idea of like spectral resolution we should be advocating for, or kind of what sort of instrument setups to go with the IFS.
Honestly, that's a great question. I will say that all the data I've shown you, most of it is the medium resolution, so R of 1,000 with near spec on JWST. I know near spec also does, the almost 3,000 resolution, and then Prism's about R of 100. I think, I don't know if it's feasible to get even better than R of 3,000. I'm sure massive star people would probably like cry tears of joy if they were able to get something of high resolution on HWO. I think personally, from my experience with near spec IFS, and I'm one of those data people, right, who's been like, we were some of the first people to reduce IFS data. We had to go through all of the pain and turmoil so that y'all don't have to. Um, I will say I think it's actually R of 1,000 and R of 3,000 are really good. Like I think they have they're the right balance of you get enough spatial resolution and spectral resolution, but then you also have enough throughput because if you break it into many more pieces, it's going to be harder and harder for the fainter stuff. And so I think those are actually really good balances. And even the prism, honestly, even though it's R of 100, you could see it as like just a ton of narrow bands put together in imaging. I think that's a good range. I mean, I obviously, if there could be high resolution, I would love that. But I think those are really good balances of, trying to get your throughput versus trying to get, the detail that you need for, kinematics versus, SED, all of that. So I don't know if that answers your question, but that's kind of where my brain is at.
Oh, absolutely. Thank you.
Yeah.
Okay. Good to
Hi,
see you.
Taylor. Yeah, thanks for the great talk. Yeah. I have a question about, so you previously, I mean, we've been thinking about the photometry is useful because it's cheap, while the spectroscopy is valuable. So, I mean, some people trying to use spectroscopic data to calibrate and improve the sensitivity analysis, something like that, to improve the use of photometric data. And also, at this time, more of spatially resolved FPD fitting also become very popular with JWST. And so I wonder if there is any ongoing effort to improve and calibrate the spatially resolved FPD fitting with IFU data. And do you have any anticipation in that direction?
Yeah, no, excellent question.
Yeah.
I know that, okay, so I have two answers to you. From JWST land, this is still a new telescope. We're still calibrating certain parts of it, right? I will say I'm not a JWST team member. I'm just an active user. But I I know that there is active work trying to make sure that the imaging and spectroscopy talk to each other, and they're actually both, consistent. Like the absolute flexing versus just the relative flexing being accurate. I think there's still some work that needs to be done there, which all will all be work that will benefit HWO and the development there. Um, as far as like the, having imaging pixel by pixel SCD fitting versus an IFU's and pixel by pixel SCD fitting, I think there's some beautiful work, very careful work being done by some of my colleagues at UPitt and UWashington that are trying to do this. And there's other people who also have created this. I think there's a postdoc at Space Telescope, Abdurov, who's made a pixel by pixel SCD fitting code as well. Like, so I think there's projects and people starting to work on this now that we have these type of data that we can compare to. The Prism especially being R of 100, an excellent SCD comparison to imaging. Um, there's obviously, I think, still a lot of work to be done there. And I think yeah, I think you got to make sure that you are appropriately also accounting for the PSF. And I think with imaging, that's a known thing, right? Like accounting data for the PSF and making sure that you're properly, this pixel is actually in this place on this galaxy. With near spec IFS, it is not yet well constrained, the PSF, which I mean, and because the IFS does cover from, 0.8 to 5.2 microns, the PSF is dramatically changing across those, as we know from imaging. It is not yet properly calibrated in for JWST. And so I think there's still work to be done on that. But I think that this is stuff we'll figure out. I'm hopeful within this decade. And so then this is stuff that will already be figured out that won't be an issue for hab worlds for the data plane there. So that's my hope. But yes, I think that's an excellent.
Yeah. Thank you for the answers. Yeah.
Yeah.
I just thought that, I mean, yeah, it could be the other, I mean, they're looking at such a beautiful data, all the direct observables from spectroscopy, that could be great, but also it could be useful for the other direction. Yeah.
Absolutely.
Other people. Yeah.
Yeah,
Okay.
There's a grad student that I work with, Julissa Sarmiento, who's a grad student at University of Pittsburgh, and she is actually working on the WASARC, the Redshift 5 galaxy I showed y'all, and she's trying to work on this, like this type of pixel by pixel star formation history stuff from imaging and also from the spectroscopy, and also more explicitly doing comparison of the dust values you'd interpret from the imaging versus the spectroscopy. And like it's a really interesting question, right? It is very hard though. But yeah, I think that's definitely it is a powerful thing that should be put in the other direction. And some people are just taking time.
Thank you.
Yeah.
More questions. Remember that I have a bunch in my back pocket, so everybody jump in, please. All right, I'm going to ask a easy one. Do you have H beta as well?
In which galaxy?
Any of them? Like,
Yes.
do you get a Balmer decrement?
Yes, we do.
Okay, because that dust at these redshifts is also weird.
Yes.
And so I was curious if you got maps or at least got you an indication of where stuff was. And so
Excellent.
Yeah.
Yeah.
Okay, so you do. So that's cool.
Yes, unfortunately, I don't have them in this slide deck, but
That's fine.
I do. There are definitely. It's actually really interesting. So let me go back to. I'll take you on the journey. We're gonna stare at this friend. So I have Balmer emission measured for all of these sources. That's part of the programs. All of the different programs, their goals was to make sure that that was detected.
Mhm.
But what is interesting, we're finding with this particular source, which, as I mentioned, through spectroscopy, we're finding is actually post-starburst in a lot of different ways. When you get this level of spectral resolution and spatial resolution, this is when you find the annoying minutia that we didn't have to care about before. So, people with manga and this Redshift Zero work, had to correct for, in their individual little pixels, correct for things like stellar attenuation
Mhm.
before they do their, Balmer decrement dust corrections. And we don't necessarily have to care as much about that at higher redshifts when we have this single spectrum, because again, as I said, everything's kind of globally averaged. But what I've been having to like cry over for the past year with this particular galaxy is trying to do very careful work because we're seeing indications of stellar attenuation in this galaxy, and it changes across the galaxy.
Mhm.
And so we're having to like individually compare regions to the photometry to try and infer what the amount of stellar attenuation might be so that we can correct for it and then do our Balmer decrements. And so it's this very intensive process. But we absolutely have that as our comparison. I think for this source, it goes up to about 1 magnitude in the color excess, EB minus V in some regions. But yes, there's a twofold problem now, where you get this amazing amount of data and now you have to do two things instead of one. But yes, we
Well,
absolutely have that.
yeah, because there's a factor two between what you get from the Balmer decrement and what you get from SED fits or like basically what the stellar continuum sees.
Exactly.
So I was curious if that was still the case at high redshift.
Yes, asterisk, right?
Okay,
So
cool.
like, yes, but then there's the asterisks of like, you got to make sure that everything's been properly accounted for and corrected. But I would say that I think we're, in some cases at least, still technically seeing that. Yeah.
Cool. Okay, so that was my first question. I have another one, but I want to open the room to anybody else who wants, like, there's so much you can learn from these sources, right? So does anybody else have a question about lensing sources? Going once, going twice, and then I'm going to just ask that the second question. Um, so you can learn stuff about the lensing galaxy as well, right? The CGM of that. do you see absorption features that actually correspond to the eye here of Mike Wazowski? Or
Yeah. So we actually, I think I can show you, okay, which direction we're going. I wonder if it would be here. Okay, unfortunately, it's not clear enough here. But what's interesting is, yes, we absolutely, first of all, the BCG here, the big bright eyeball for their little WAS galaxy, is really bright. The way it bleeds out from its center is, it's incredibly extended, as far as the way the light stretches. And we absolutely have the light contaminating the IFS data we have for this galaxy. And so at first we didn't realize that. We were seeing like these weird bumps, what almost looked like a rest frame 3.3 paw feature at one point, and we were panicking. But it turns out, no, this is actually like the continuum is being impacted, especially on the blue end, by the shape of the BCG spectrum.
yeah,
And then also we're seeing dust emission in certain parts of the BCG that are not from this galaxy, but they're popping up in our galaxy spectra. And so it is absolutely something that we're fitting in and subtracting right now. But that is also, like, as you note, that was not the crux in the science case of this particular program, yet that is also an amazing wealth of data that someone else can take and like run with, right?
yeah,
Same thing with the other programs. It would take me too long to slew back to them, but the templates ERS program, for at least two of those sources, the HST dark ones, we have their galaxy lenses versus galaxy cluster lenses. And so the lens, just like this one, is in the very center.
yep.
And so there is actually some undergrads and grad students currently working from the templates program on studies of those galaxies and looking at the gorgeous absorption lines, like the CO bands and stuff. It's beautiful. And so this is definitely like a wealth of data that exceeds what is just the science case from the program.
Cool. All right. Um, this, yeah, galaxy lenses. It's always like, what are you studying the source of the lens, right? And the answer can be
Exactly.
yes. So that's really cool. Okay, opening up the room one more time before I start talking the whole time, which I'm trying to avoid.
Okay, I'll go back to an animation so we can stare at that.
Okay.
All right.
Yeah.
I've got a question,
Yes.
Benny.
Go for it.
Great talk, Taylor. This was super interesting. My question was sort of a follow-up on the Benny's last one, that last image you were at. Um, so you answered part of the question I was going to ask, which is like, is the source, the giant eyeballs emission contaminating uh, your object? And it is. My follow-up question is, have you made IFS or plan to make IFS observations of the counter image?
Great question.
Um, like, yeah, just say more about that because if it's I'm really curious about the reprojection of that too because uh of the object because if that's the case then we're getting all this really interesting star formation history emission line mapping stuff at potentially two different look back times.
Yes.
And so my next follow-up question, the final part of that question is how well do you actually know like between your stretched image and your counter image sort of like which knot corresponds? Do you know what I mean?
Yes, I do. Excellent question. Um,
Thank you.
yes. So as of right now, we've not yet put in at like a request for time for the counter image. I think mostly because we're worried that like they'll be like, you have enough data, go away. But
Sure.
it would be like if we could, that would be amazing because like you can even see in this image, it's much smaller, right? And generally, like I mentioned, in these types of lensing events, you have the counter images almost looks like some form of the source plane, the original shape of the galaxy. And so your question about if it's clear at all if we can like map the big smile back to that little knot, this is where knowing the redshift of every single source and its extent in this field, and then also the velocity information I showed towards the end of my talk, this is where that is really important for our lens modelers because that will directly inform how well we're able to reproduce the source plane. But the counter image is also a vital component of that, and I really do wish we had pointed an IFS there. Um, so yeah, short answer is no, we don't have data. Would love data. I don't know if they'll give it to me. If anyone wants to put that proposal, let me know. But yes, with all the information that we do have, it actually would be it is not impossible for us to backtrack this in a way that feels almost accurate, right? especially comparing with the imaging we have, the counter image. But it is hard. I mean, lensing it's challenging. Um, but this is, yeah, I think this is the best we could do. And as I said before, there's actually, if I could, oh, can I annotate? Oh, this is Zoom. Yes. Okay. I'm going to annotate. So if we had a lensing map, I'm going to do a bad job at this and I apologize. I'm going to draw the critical curve and it goes there and then it goes out and does that. It's something like this, if I remember correctly. So it's this weird wiggle. For people not familiar with looking at lensing, this is kind of describing the way that the light is being warped. And so what you could see is, and I showed this in one of my images, I think. I think it's right there. These lines I've just put down, these yellow lines, are actually dividing this arc into three pieces. And based on the way that the light is being warped or lensed through this whole system, especially along the critical curve, we actually have three images of the same images, you could think, just kind of mirrored or warped in a certain way, but like it's still the same light in these three different regions. And so we're kind of getting three different pictures of the same thing. It's like different angles of the face, you could imagine. And then we're comparing back to the counter image. And so that is also how this is, like a pretty straightforward like it's hard, but it's a straightforward way to try and backtrack this. So we have all the information we need, actually. I don't know if that fully answers your question, but
It does. You've definitely you've definitely described how this is a very complicated thing going on here. But
yeah.
sounds like if you using, you spoke about your modelers. It sounds like using kinematics, you can sort of figure out, or the modelers can maybe guess what clump corresponds to what clump. That's what it
Yes.
sounds like.
Exactly. And you can kind of like
Interesting.
also pick apart, like, this one is really blue. I believe that one actually might be this. Like, so there's ways that you
Sure.
could, just by eye, even with coloring, try and, figure that out. But yes, the velocity information is really critical here because there's some ways that people do this modeling where they also do something called forward modeling, where they start with the source and like what the galaxy should look like, and they start adding knots of like light in some places and see how it propagates through the lens model and what it looks like at the end. And so it's almost like a trying to make the image you see versus taking the image you see and going back to the original. And so there's a few different ways people approach doing this, and we actually have two people on the team doing both. So um, it's they do their whole career is just doing that, and that's not something I want to do. So I've been very grateful that this is what they enjoy doing.
Awesome. Thanks, Taylor.
Yeah.
Yeah, the student work on lensing, but just to do the halo profiles. And so the very first model you do in an afternoon, it's very quick.
Yes.
And then the second model is 6 months. So it is the kind of thing where it's like, yeah, now you want detail. And so I feel like spectroscopy is sort of in that same category. It's like I can get a line strength and now I want to get a line ratio that I can trust. And it's like, oh, now I have to, all these other things come out the woodwork. Great. It's great.
Exactly.
So does anybody have any other questions? I am even running out of questions, although this is gorgeous data. It is really, yeah, you can see a lot of detail that you can then link back to the larger studies of populations that we don't have lensing for, which I
Exactly.
think is also really neat. Um, Anybody else have a thing to remark, unhinged, shout, whatever you want to do? The word was unhinged this week, I think. So,
Yes. Well, if
um,
this is helpful food for thought, something I didn't touch on, but for this particular source, um, if you want to hear me wax poetic about something that might not be real, I think we might be detecting potentially the presence of diffuse ionized gas or DIGs in this, in the regions that aren't at like the bright star forming knots, which, would be some of the first at this redshift, which is also fun.
that's really cool. Right. Awesome. Yeah, we can always learn more about these. Uh, I think at low redshift, by the way, for the UV, this is sort of restrains you to well below redshift 1,
Yes.
where you can learn these things. And so your sources are going to be very different sizes, and very so your tiny little eye view where you can learn everything about this tiny source on the sky, you suddenly are now consideration might go, we have to go wide like this. And we've done this once with Muse, and I think every
Mm.
engineer who worked on Muse is going, and we're never doing this again. Um, and so that there might be some other considerations on how to get IFU at low redshift. So there's going to be a very interesting discussion going forward, I think, doing this because suppose I think the example was to look at M51 and just look at every individual star clump and see if they're, the winds coming out of it, the ejecta, the feedback. If you're doing that with this IFU, you're going to be doing that for the rest of JWST's lifetime, right? It's just
Exactly.
you're going to have to go through the whole thing. The thing's enormous. So we're going to have a very interesting discussion trading maybe spatial resolution for spectral resolution or the other way around.
And I will say, I mean, it's a good point about the UV, and also this goes back to Annalise's question. I would say that I would also be fine with an optical Muse, like I know you just said the Muse people would be like, please no, but like a Muse like wavelength range IFU instead, or IFS instead. Because then you could potentially be doing line continuum linking light at redshift 3. You could be probing, taking advantage of anything that overlaps in the observed optical wavelengths, which could potentially, open up for more redshifts, for more science. But I do think there is definitely, I know I might be in the minority, but I do think there is definitely some power to the observed UV wavelengths. But that does, like you said, it does limit us dramatically in redshift and source type.
I mean, I'm all for it, but I'm usually the IFU user that goes, can I have a really large field of view? I don't care about spectral resolution. And I'm alone in that. So
Yes,
there's
you are.
going
I'm so sorry. I do not want that.
So yeah, that was a wonderful talk. There's a lot to be thinking about, but we should be advertising for an IFU instrument on how HWO, and like
Yes,
what
please.
would you like? Like start making your Christmas list here already. So thank you all for coming. If I don't have any more questions, no, I don't see any raised hands. So thank you so much, Taylor. That was a wonderful talk. I
Yeah,
really
thank you
enjoyed
all.
it. Thank you for coming, and see you all in the.
In
That's
the
it.
fall, I just want
In
to
the fall,
say
right.
thank you everyone for joining us this whole year. This is the last seminar we have planned for 2024 to 2025. So we're going on summer break and looking for speakers. So if you would like to give a talk or you'd like to nominate someone, just drop me an email. We'll figure that out in the summer. But we'll come back, I think, in September, hopefully. So everyone have a good summer. Bye.
Yeah.
Thank you. Bye.
Bye.
Thank you.